Okay, so we're just going to go through the last little bit of the notes from 1.1 here. So I'm going to talk really quickly through some of the vocabulary and then do an example, and I'll do some of the other examples in a second video. All right, so general solution, when we talk about solutions to differential equations, we have some different kinds. So we have general solutions, particular solutions, and singular solutions. General solution is going to involve some parameters. So remember that those are generally constants, but they're constants that might take on different values in different problems. Represents a family of solutions to a differential equation. So it may not represent all solutions to the differential equation, but it's the most general form. So in the prior example we looked at, y equals c e to the 3t could possibly be an example of a general solution to a differential equation. It's got a parameter. It involves a whole family of equations that are solutions to that differential equation. In that particular problem, though, it is not actually the most general solution to that differential equation because there are more general forms that encompass more solutions to the differential equation. So we will look at some theorems that kind of tell us how do you know when you have the most general form. So this one is what often general solutions look like, but in that previous example, actually, let me scroll back up here. The most general form for that one is y equals c1 e to the 3t plus c2t e to the 3t is the most general form. And so we wouldn't know that until we learn some theorems. So we'll learn those as we go throughout the semester. Okay, particular solution is one solution to a differential equation. So often that involves finding values for the parameters. And so sometimes you're given some information that allows you to do that. So one way that you're sometimes given some information that allows you to find the parameters is you're given what's called an initial condition. So initial condition, sometimes called initial values. Specific values for the dependent variable and or its derivatives at a specific value of the independent variable. All right, so if you look down here, actually we've got a differential equation, first order differential equation. We've got a solution here which involves a parameter, so perhaps that is a general solution. It's hard to tell until we learn some theorems whether that actually is a general solution or not. And what we have here are some values for the variables. And so these are what are called initial conditions. They're called initial conditions often because they happen at input equals 0, but not always. And altogether, what we have here, the other vocabulary word up at the top there, is when you have a differential equation and an initial condition given, that's called an initial value problem. So it's just a differential equation plus initial condition. All right, so singular solution, we'll look at an example. Actually, one of these later examples has one. Our textbook doesn't talk about it until 1.4. Singular solutions are sort of like these separate isolated solutions. They do satisfy the differential equation, but they don't fit the form of the general solution. So they're kind of interesting little strange solutions and something to kind of be careful about. So we'll see that really as we keep going. We'll see it more in 1.4. When you talk about solutions to differential equations, you're sometimes asked in the homework to give your solution in explicit or implicit form, and that's really just kind of the algebra here. It's a solution to the differential equation, solve for the dependent variable, that's explicit, or if it's not solved for the dependent variable, then implicit. So generally we want explicit ones if we can get them. All right, and then this next part here, this is another thing that sometimes students have a really hard time with, so we will keep hitting it over and over and over again until we all get it. Interval of existence. So interval of existence of a solution, values for the independent or input variable for which the differential equation and initial condition are satisfied. So the big tricky part about that is that a function has to be continuous in order to be differentiable. So when we talk about interval of existence, we cannot go across a discontinuity, cannot be a solution across a discontinuity. So you have to be careful about that. So we'll look at some examples in some of these later examples here. All right, so let's just look at this first example, and then in another video I'll do the other examples here. Okay, so we are given a solution here. We could verify that this is a solution as we did in some of the other ones. Just take an appropriate derivative, first derivative, plug it into the differential equation, and make sure it works. So in the textbook, unless they ask you to verify it as a solution, you can assume that what they're handing you really does work. But what we're asked to do here is to find the particular solution satisfying the initial condition and give the interval of existence. So actually for this part we're really just doing some algebra. In some ways the thing to learn here is the vocabulary and what it is they're asking you to do, but the math isn't really hard math. You basically just need to find the c values so that y of 0 equals -1. And one of the things I want to emphasize here is what y of 0 equals -1 really means. This is actually a point, 0, -1, that is on the graph of the solution curve. Right, so input, output, that's what we've got here. And so we need to find the c so that basically that curve, you can maybe think about what the graph of that solution looks like, because it's pretty simple functions, so that it actually passes through this point, 0, -1. All right, so we're really just going to be doing some algebra. We're just going to be putting in 0 for x and -1 for y, and we'll just put those in and figure out what is the appropriate c value for that. So we'll have -1 equals c e to the 3 times 0 plus 1, and then just do the algebra. -1 equals c times e to the 0 is 1, so that all just collapses to c plus 1, subtract 1 from both sides, so we get -2 equals c. So we've done all the math we really need to do. It's just a matter of writing the solution. This curve, so this is a solution curve to the differential equation, and it does pass through the point 0, -1. We're going to look at some graphs in section 1.3, so we'll kind of think about that in terms of graphs a little bit more. All right, I'm going to do some other examples in the next video.